Hi, my name is Sunil, and welcome to the first lecture in our series on artificial intelligence in railways. So, today we are going to explore one of the most transformative technologies that has entered railway industries right now. Artificial intelligence is not longer a future concept. It's not something that is going to come. It's already here and it's already been implemented in many major projects in railways around the world. AI has helped us detect the faults earlier, respond faster to the disruptions, and make decisions safer. So, for the system assurance engineers and students, you need to understand how AI works. Only when you'll be able to understand how AI is working, you'll be able to assure it, you'll be able to validate it, and then you'll be able to build safety cases around it. So, this lecture will cover three main points. At first, I will explain you how AI works in a totally non-technical terms. Second part of the lecture, I will discuss a few examples where AI has already been implemented and it's helping the organizations for maintenance, safety, and operations. And towards the end of the lecture, we'll discuss about the challenges that system assurance is facing and why the traditional standards like 50126, 129, 128, they still apply, but these standards have to be adopted for AI. By the end of the lecture, we will be able to have a solid foundation which will help us for the deeper dive, and we'll discuss topics in our coming lectures where we'll discuss about standards, risk assessment, and implementation. Why railways are a safety critical domain? So let me set the context here. Railways operate under a unique set of constraints that most other industries do not face. There's a reason that why railways are considered as a safety critical domain. The first one is the high consequences. A single derailment can kill dozens of people, it can damage the environment, it can disrupt other transportations in the region. This is not a made up fact. We all know that it happens on day-to-day basis. So, because the stakes are so high, railways maintain some of the world's most rigorous standards related to safety. The point number one, I think, why the railways are safety critical domains. Second one being the complexity. So, railway systems are so complex that there are so many systems that have to work in a perfect synergy to move the train from one place to another. We have systems like signaling, rolling stock, other infrastructure, and even the human operators. So, a failure in one domain, for example, in track geometry, that can cascade into a safety incident if the other systems like signaling do not catch up. This means we need a multiple layer of protection. And the third reason why I think railways are safety critical domain is about its regulations. So every change in the railway systems, whether it's about new technology, new signals, new softwares update, a new maintenance procedure, everything has to be justified, it should be documented and demonstrated to be safe. In Europe, this is done using Senelec standards like 50126 and 50129, which is covering RAMs and safety cases. But I think the same standards are implemented most of the railways around the world. So, into this highly regulated, safety critical environment, we are introducing AI. Let me demystify AI in a bit. At its core, AI is a computer system that learns from data and makes decisions or predictions without being explicitly programmed with the rules. So let's do a basic comparison. So when we are building a maintenance scheduling system old way in a traditional software environment, we have to set up the rules. We have to write the rules in the programming. For example, if a bearing has been in service for 5 years, scheduled for replacement. That's explicit, that's deterministic and easy to test. You know exactly what the system will do given any input. Now, if we are building the same system using AI, we don't write any rules. Instead of writing the rules explicitly, we will just show the system thousands of examples of bearings with these characteristics. How long they have been in service, how much was the vibration they exhibit, what temperature they ran on, and whether they actually failed or did not fail over the passage of time. The AI system learns pattern from those examples and builds a model. So when a new bearing comes, the model predicts its likelihood of failure. Same input might yield a different prediction depending on model's internal state. It's probabilistic, it's not deterministic. This is incredibly powerful for complex problems, but it's also a new source of uncertainties in our systems. So these are the uncertainties that we need to understand and we need to assure. That's where the challenges lies. Currently, all our softwares used in the railway industries were always deterministic. We knew what is the input and what is the output. There's a certain set of rules that these softwares will be operated on. So we call it a deterministic approach. So current softwares, all of them, 100% of those softwares are all deterministic. When we give in any input, we knew what the output will come. AI at its fundamental core is not deterministic, it's a probabilistic technology. So, all the softwares that will be using AI are probabilistic, they will operate on the probability of the outcome. So, that makes the system intelligent when it's learning from all its inputs and then measuring the output based on the training it has taken from the inputs. So, these are the two key terms we'll be using frequently in our coming lectures. First one being deterministic, and second one being probabilistic. This is the time we understand the difference between what is deterministic, what is probabilistic. Only then we'll be able to know the difference, we'll be able to adopt our current standards into AI. Because till date, all the softwares, that's why we were able to assure those softwares for over past few decades, because these softwares were working on a fundamental concept of deterministic systems. So this is the challenge that we are unpacking over the next few lectures. Okay, let's discuss about types of AIs being used in railways right now. So railways use different flavor of AI depending on the problems. So we are going to discuss four here. First one being the machine learning model. You have to provide model a historical data and you want model to predict something for you. For example, you give the wheel's vibration signature, its age and axle temperature, and the system is going to predict when is it going to fail. So you train a model on past wheels and failures and it will learn the pattern and then give you the prediction according to that learning. So major advantages for this kind of AI is that you can scale it to a large data set and you can capture the complex nonlinear relationships. And the major challenge we are facing in implementation of this kind of AI in railways is a quality of data. So the data that should be used to train this kind of model needs to be the best quality data. Only then the system will be giving the proper significant results. So that's the challenge. Second AI that we are using nowadays in railways around the world is deep learning. That is where we are giving sequence of complex images to a system, to a model, and it's learning using the images. For example, if you want to detect a crack in railway surface, you feed thousands of rail images to this AI model. Some of the images are with the cracks and some of the images are without the cracks. Using those images, it will learn to recognize the crack patterns. Advantage in this kind of AI is that they are really high accurate for visual tasks and they are able to learn the features automatically. The training is fast as well. The challenge is that you need a lot of training data and often like the system acts like a black box. It will learn from the pattern, it will make its final decision, but you will not know that why the decision was made. So it really depends on how the system is learning from its training data. But over the past examples, in the pilot projects, it has shown over 95% of accuracy in the projects like where it was used to detect the cracks in the rail. The third kind of AI that is being used nowadays in railways is the data analytics AI. These are the statistical models to detect the anomalies. For example, this continuous streaming vibration data is coming from the track section and it will detect the anomaly in the algorithm. And when it's going to detect any anomaly, it's going to flag it as some defect is emerging. So advantage for this kind of AI is that these are often more interpretable. You can learn from it. You can actually interpret these kind of models, and the training data required to train this kind of AI is quite low in terms of quantity. You don't need like a massive amount of data to train this kind of models. But challenge we are facing with this kind of AI is that as compared to the other AI systems, these are less powerful for complex systems. And last one being reinforcement learning. This is one of the most complex AI that I have, in my personal opinion, this is one of the most complex AI that we are using in railways nowadays. Reinforcement learning, AI agent learns through trial and error about the system. We have examples like digital twins, where the system assets are having a exact replica, and the AI agent will learn through trial and error, and it will respond to the reward system. So if the reward is given, if it performs some activity on its replica, and the reward is given as a good action, it will duplicate that action in the real life railways as well. These are mainly used to design maintenance plans. The agent will learn like which maintenance actions will minimize the long-term costs and failures. The advantage is that, as I mentioned, this is the most sophisticated AI we are using currently in railways. The challenge we are facing is it's quite slow in the training, and also it's risky when the reward system for training the AI does not align with the real life, real goals in the railways. This should be trained in a quality data, and the reward system should always have a check for its algorithm. So all of these are in use in railways nowadays. Up next, we are going to learn about the key characteristics of AI. So in the key characteristics of AI systems, I want to highlight 4 key characteristics that make AI different from traditional softwares. And as a result, it complicates our assurance process. First one being learning. So AI systems are data hungry. They improve as you feed them more data. That's a huge advantage. For example, a predictive maintenance model give us better results if we give it more examples to train. So it will be able to spot a failing component, for example, a bearing, if we are giving more examples to the system to learn from it. But it's also a bit risky, because if your training data is biased, for instance, if 90% of your wheel defect images come from one particular line under one particular climate, then the model will be biased towards that context. When deployed on a different line with a different condition, it may fail. This is why data governance is a critical part of AI assurance. Second is non-determinism. I think we have discussed it previously in 2 slides before, that traditional softwares are deterministic. Given the same input, it will always give the same output. That's a fundamental assumption of testing and validation. AI systems are probabilistic at its core. A deep learning model might output 90% probability that a rail section has a critical fault, or 85% probability that a bearing will fail in 3 weeks. The same input run twice might also give a different output, because this is how the neural networks operate. The concept of neural networks is based on its internal randomness and numerical precision data. So for safety critical system, this is a challenge. How do we assure something that's inherently probabilistic in its nature? That's a question we will tackle in later lectures. Third characteristic is about its opacity. So many AI systems, especially deep neural networks, act like a black box. We can't easily point out the specific weight or specific logic to say, for example, here's why the decision was made. We cannot pinpoint that particular line of code, or we cannot reason it out that why this decision was made. Unlike in traditional software programs, you can trace through the logic. If condition X, then action Y. But with neural networks, there are thousands or millions of weights, and the decision emerges from a complex interaction across those layers. Exactly how our brain works based on neurons. This has particular consequences for assurance. If an AI system makes a wrong decisions, for example, it misses a critical wheel defect, how do you diagnose why? You can't just step in and then go through the code. You need explainability tools, and those are not always mature. For safety engineers, this means you need extra scrutiny, testing, validation on diverse data, and monitoring in operations to catch failures you didn't anticipate. Fourth one is its robustness under variation. AI models are trained on a dataset representing some set of condition. If condition change, for example, new type of rolling stock comes in, new track geometry appears, new climate patterns, the model may not perform well. This is called distributional shift. In other words, drift. Imagine an AI model trained to predict wheel defects using data from UK railways. In Europe, the weather is cold. The model has seen winter condition, Europe tracked specification, their own train fleets. Now, deploy that system in, let's say, Middle Eastern railways with year-round warm weather, different track standards, and different rolling stock. The model might perform poorly because the data distribution is different. This is why validation and ongoing monitoring are so critical. We can't just train a model once and forget about it. So, despite all these uncertainties and its probabilistic nature, why are railways adopting to AI? There are two major factors which we'll be discussing. There are two major drivers. First one being cost drivers, and second one being the safety driver. For the cost drivers, we have three examples. First one is predictive maintenance instead of preventive maintenance. Traditionally, railways replace components on fixed schedules. All wheels get replaced every 5 years. All bearing get replaced every 10 years, regardless of its condition. It's a conservative approach and it's safe, but it's wasteful. AI-powered condition monitoring lets you inspect continuously, detect degradation earlier, and replace only when it's needed. So the results have shown that there is 20 to 30% reduction in maintenance costs, longer component lifespans, and higher schedule precision. Second factor, which impacts the cost, is the continuous inspection instead of schedules. Manual rail inspection is a labor-intense process. For example, a team will walk for a few kilometers per hour with visual inspection, covering mainly 20 kilometers per day, 20 to 30 kilometers per day. But if you're using an AI-powered machine vision system mounted on trains that can inspect the main line, it can easily cover 3 to 400 kilometers per shift. That's a 15 times faster coverage per unit of person effort. And AI doesn't get tired or distracted. So detection is more consistent. Third major cost factor that we can think of is the optimized operations. Trains operate in a complex network. Any delay, AI-based traffic management can read out trains faster, reduce conflicts, and it can also recover the disruption much more quicker. As a result, it will get better punctuality, happy customers, and reduced energy consumption. These are compelling business drivers. Every railway wants to cut costs and improve reliability. But cost alone doesn't justify deploying something risky. We also need safety improvements. That's where we'll go into the safety drivers for adopting AI into railways. So, beyond cost, there are genuine safety improvements. So, first one is early fault detection. An AI-powered condition monitoring system can detect subtle changes in bearing vibration or wheel geometry weeks, often months before the defect becomes critical. This gives maintenance teams time to plan and intervene rather than dealing with the emergency detachment. Fewer emergency detachment means more reliable service and fewer risky situations. Second factor for the safety driver is its hazard detection and prevention. An example is AI vision systems can detect obstacle at level crossing in real times. It can trigger warning, and in some cases, it can initiate the speed reduction that allow the train to stop as well. Similarly, AI-powered CCTV can detect trespassers before they step in front of the train. These are direct safety improvement that has saved countless lives over the past years. Third factor for safety is its faster incident learning. So railways have thousands of incident reports every year. Traditionally, safety analyst will manually review the incident report. He will categorize it, and then that becomes overall a slow process. AI systems can auto-classify, extract key information, and surface trends. If trespassers incidents spike at a particular location, AI can flag it within days instead of months. This accelerates corrective actions. So, railways have both business as well as safety concerns to deploy AI. But with that opportunity, some responsibility comes as well. We must assure that the AI itself is safe, reliable, and trustworthy. So let me give you a concrete example of AI in maintenance. Like machine vision inspection is one of the most mature applications in railways right now. The idea is simple. We're going to mount high-resolution cameras on train or inspection vehicle. As the train travels at normal speed or slightly reduced speed, the cameras will continuously capture detailed image of rail surface. It will also capture the images of wheel, catenaries, and track geometry. So these images are either real time or in offline. They are processed using deep learning models, which are trained on various defects over the past many years using the training data. And it can detect the defects like cracks, spalling, corroded fasteners, or misaligned lanes, catenary wears, or wheel flats. So the performance of this system is impressive. In the pilot projects, it was found that detection accuracy is 95 to 98% for many defects. A trained inspector might achieve 75 to 80% accuracy in these kind of detections. So here, AI clearly beats that. Importantly, AI can run 24/7 without any fatigue. So a single train can inspect thousands of kilometers per week, whereas a manual inspector, he might be able to cover 100 to 200 kilometers per week. So that is the first driving factor where AI has completely overperformed us. Second is the cost impact. So by detecting defects earlier and enabling the targeted interventions, railways have saved over 20% in the maintenance costs over the years. Maintenance has inherently become more predictive instead of reactive now. These are the two important performance matrices where we can see that the AI has clearly outperformed our manual processes. But this is where the assurance challenges lies. The system is trained on a defect images from a specific route, on a specific train, on a specific kind of rolling stock, and during a specific season. If you deploy it on a different line with a different rail specification or a different climate, does it perform as well? That's a question we must ask in safety case. You must validate on representative data and monitor performance in operation continuously. Okay, another high impact example, let's discuss about the condition monitoring of wheel sets. Wheel defects are major source of rail accidents around the world. A flat or cracked wheel can cause derailment. Traditionally, wheels are inspected by eye at depots and replaced on a fixed schedule. But now, wheel impact load detectors. Whilst these are the detectors mounted on trackside, they will measure the shock each wheel produces when it passes. So, large shock indicates wheel defects. Combine that data with the vibration sensor and temperature data, AI model can predict wheel degradation with 90 to 95% accuracy. So, practical benefit here is that instead of replacing the wheel on every 5-year schedule, depots can replace them when AI predicts degradation. As a result, 30% fewer unscheduled wheel removals, that means fewer emergency detachments, and wheels that are still good can get a longer life. That saves money and availability is improved. From the assurance point of view, these kind of models must be validated and the data should be trained on diverse wheel types, not only on the wheel signature, but on track geometry, on an environment condition, and other factors. What will happen if a new wheel supplier introduces an alloy that will slightly be different in acoustic signature of the wheel? The model might misinterpret shock. That's why monitoring and retraining are essential in these kinds of systems. That's our challenge in assurance. Another example, let's discuss a more sophisticated AI system, digital twin with reinforcement learning. So a digital twin is a virtual model of a physical asset. In this case, let's discuss, let's say, a section of a track. Sensors on the real track will feed data into its digital twin, keeping the model synchronized with the reality. So an AI agent using the reinforcement learning will learn what maintenance actions that will help in minimize long-term costs while preventing failures. So this is how the digital twin model, a digital twin system works based on the principle of reinforcement learning. So the reinforcement learning model will try to have a different maintenance action in simulation, not on the real track, but only in the simulation. It will have different maintenance action performed and it will receive rewards based on the cost and failure prevented. It will gradually learn the optimal maintenance policy for that particular track section, which we have created a replica in using our digital twin. For example, it might learn that for this track section, replacing the sleepers every 2.5 years instead of every 3 years prevents 80% of the failure at only 10% extra cost. A real life example is in one of the European railways. They have implemented this and reported that 21% fewer maintenance activities, 68% reduction in the defects, and 15% cost savings over 2 years. So, when this system was implemented in the European railways, they have seen these significant, impressive results over the past 2 years. The system has learned policies that human schedulers hadn't even thought of. But here lies the assurance challenge. These reinforcement learning models can find counterintuitive solutions that are hard to explain. You must validate that reinforcement learning agent it respects safety constraints. For example, what is the maximum acceptable failure rate and what is the minimum track geometry standards? So these factors should be considered while training these kind of models. So if the reward function is wrong, the agent might optimize for cost for the expense of safety. Vetting the reinforcement learning model is a really specialized skill that we should be focusing on as a system assurance engineers and system assurance specialists. Now let's move to safety and discuss level crossing obstacle detection. At a level crossing, a vehicle or a person on a track is a catastrophic hazard. Traditionally, level crossings are protected by barriers and warning lights. Barriers can be automatic or semi automatic. But if a car stalls on a crossing or a person climbs above the barrier, the risk will always remain. So, AI powered vision systems can detect obstacles in real time. Let's discuss how it works. In these systems, cameras are mounted on level crossing, sending their feed continuously to the AI model, and the model detects if there is a vehicle present on the crossing, if there's a person, or even there's a fallen object like a tree. So, if an obstacle is detected, the system will trigger audible warnings. It will issue visual alerts for nearby traffic, as well as sends the alert to rail operations. In advanced systems, it can even initiate automatic speed reduction as well. During the pilot projects, it was found that the detection accuracy in these kind of systems is above 96% for vehicles and persons. False positive rate was less than 1%, and latency was less than a second. In 0.5 seconds, they were able to get the signal. They were able to detect the obstacle on the level crossing, which is fast enough to allow proactive action. But it has a safety critical challenge. Visual systems can easily be fooled by weather, if it's rain or fog or snow, or even with glare or unusual object. The system must degrade gracefully. If the cameras are blocked or fail, the crossing must revert to safe state. That means the barriers should be closed, and this is a safety related function as per EN 50129, which requires SIL validation. Another safety related application we have is a CCTV based trespassing detection system. So, railways around the world, they lose lives to trespassers, either a person deliberately accessing the track or a person in danger. That means standing too close to platform edge or climbing infrastructure in the railways on the station. 24/7 human monitoring is not practical. AI can monitor CCTV footage and it can detect unsafe conditions. So key benefits here are it can send alert to the control rooms when the trespasser is detected. That can enable fast response, either send the staff to the scene or reduce the speed. And also the system can have 24/7 coverage without fatigue. But the human factors and ethical considerations are critical here. In Rail Safety and Standard Boards, in one of their research, they found that the CCTV plus AI systems designed for trespass detection was flagging the young man in hoodies as a hazard. Investigation revealed that the model has learned to use hoodies as a proxy for risk. So where they see a person wearing the hoodie, the model will automatically consider it as a risk because the training data happen to have the overrepresentation of that kind of demographic where during the trespassing, the person was wearing hoodies. So model has learned hoodie as a deciding factor for flagging a hazard for trespassing. So this is bias. It's unfair and it's potentially discriminatory. So they came up with the solution. They developed the explainability tools that will let analysts see what features the AI is using in its decisions. In this case, they were able to reduce the weightage of hoodies in the model and added some continuous monitoring for bias. This is where the transparency and ethics come in. These are the topics we'll be discussing in detail in our future sessions. So let's discuss a third safety application, that is AI for incident analysis. So railways around the world generate thousands of incidents and near miss reports every year. Incident reports are narratives. For example, like a person slipped on platform 3 at station X at 2:30 p.m. on a wet day. Traditionally, the safety analyst will manually read it and categorize these reports, which is a slow process. By the time trends will emerge, it's often weeks or months later. At Rail Safety and Standard Board, they were able to develop a platform called Safe Insight. They were able to automate this using natural language processing model, NLP model. So this model automatically classifies reports, extract key informations like location, severity, type of incident, and then link it back to the incidents. Each incident links are related and system is able to monitor it. So this machine learning model that can surface trends like platform edge incidents have increased 15% over past years at station with greater than 500 passengers per day. Now this is an actionable trend that AI was able to surface within days instead of months. Impact here would be the safety teams can now intervene faster if the new hazard is emerging. Standards and procedures can be updated based on faster feedback. Although this kind of system is not directly safety critical system, but AI must accurately classify documents and all its reports. Misclassification could lead to missed signals. So humans still interpret the findings. So assurance focuses on classification accuracy and maintaining its auditability. Now let's look at the operations side. The Intelligent Junction Optimizer is an excellent example of human AI teaming up in a high-stake environment. So this scenario was part of the research by RSSB, Rail Safety and Standard Boards in UK, where a freight train that failed on a major junction, blocking the key approaching lines. 12 passengers and freight trains were in queue. Line controller has minutes to decide how to move trains and minimize delays. The AI system, Intelligent Junction Optimizer IJO, has accessed the timetable, train performances data, line capacity, and the rule. It analyzes all possible routing and regulation options and proposes 3 ranked solutions, each with clear trade-off. Solution 1 was to minimize delay, but that requires diverting the passenger trains. That has a higher passenger impact. Solution 2 was to spread delays more evenly. And solution 3 was to minimize energy consumption by increasing delay by 20 minutes. So controller in this case was not passive. He was part of the decision-making process. He reviews the proposals given to him by AI, applies his local knowledge, and modifies the solution. Because he knew the train which was supposed to come for relief route was not clear. It was not available because it was substituted this morning by rolling stock team. So he modified the solution. He simulates the hybrid plan confidently, then he implemented it. Why this kind of AI design is good? First one, AI amplifies human decision making, but it doesn't replace it. The AI was able to give the possible solutions, but it did not enforce the route controller, to implement it. The human retains the authority and responsibility because he had a wider view of what's happening in the line. So he had the authority and he was able to take his actions responsibly. Mental model was aligned. The controller understands the trade-off and he can challenge the solution proposed by AI. And most importantly, AI was able to handle the computational heavy lifting by calculating all the routes, timetable, line capacity and rules and suggest the solutions. And human, the line controller in this example, was able to apply his expertise and context. This is a gold standard for safety critical AI in operations. We will revisit this principle in later part of our session in our human factor lecture. This brings us to the core assurance challenge. For decades, rail safety engineering has been based on set of assumptions. Let's discuss few of the assumptions. First one is determinism. Traditional hardware and softwares are deterministic. A single relay either works or fails. A braking algorithm, given the same input, always produces the same outputs. We can test a finite set of scenarios and be confident the system will behave as designed. But with the AI, these assumptions break. AI models are often probabilistic. A deep learning model outputs a probability, not a binary decision. The same input might yield slightly different output due to numerical precisions or stochasticity in training. For safety engineers, this is so uncomfortable. How do you assure something probabilistic? Second assumption is testability. Traditionally, we validate software by testing it on a comprehensive set of test cases. If it passes, we are confident it will work in operations. But with the AI, the test set is often much smaller than the space of possible real life inputs. There's a phenomenon called the test train gap. The model might perform at 95% accuracy on test data, but 80% on real operations data because the distribution differs. You can't test your way to accuracy as easy. Third assumption is explainability. Traditionally, the softwares we were using over the decades, we were able to trace through logic. We were able to see all the inputs and the outputs and all the rule sets given in the software. AI, especially deep learning, is opaque. Why did the model classify this crack as critical? You can't point out a specific line of code. Why did the model identify this person as a hazard? You cannot clearly identify a specific line of code in the model where it went wrong. Another assumption we have is about static behavior. So once deployed, traditional software doesn't change. Unless there is a security patch or something, they always remain the same. AI models can learn from new data. It can be retrained, and that breaks the configuration control. Another assumption is about the failure modes. Traditionally, system fail due to hardware faults, which is predictable from physics, or it will fail due to the code bugs, which is traceable to the root cause. So all the failures traditionally were either hardware or software based. Hardware, we can trace it down to the physical laws, and software, we can trace it down to the root cause using lines of codes used to develop that software. But AI will fail in numerous new ways. There will be bias in training data, there will be drift over time, there will be human AI miscommunications, and there will be distribution shifts as well. So these are the real challenges, but the standards still apply. EN 50126 still requires hazard analysis and risk analysis, and FMEA and RAMS planning. EN 50128 still requires rigorous software development. EN 50129 still requires safety case. We just have to be AI aware in how we do it. Now, let's be clear. EN 50126, EN 50128, and EN 50129 still apply to AI in railways. They are not obsolete. EN 50126 defines RAM's life cycle from concept through decommissioning. It mandates hazard analysis and risk assessment. In other words, we call it HARA, HARA, and continuous improvement. These are exactly what you need for AI. Another standard we have is EN 50128, the existing standard, that specifies the disciplined software development process. That includes requirements, traceability, VNV, like verification and validation, and tool qualification. AI systems are implemented in software, so EN 128 applies here. You just need to extend it for AI specific consideration. For example, training data quality is now a tool and must be qualified. Another major standard we have for system assurance is EN 50129 that defines the structure of safety case and technical safety reports. You still need a safety case for AI. You just need to argue explicitly how the AI contributes to safety, what its failure modes are, and how they are mitigated. So, what's new regarding AI we have? First one is IEC 42001. That standard explains about AI management system. It provides the guidance framework for developing and maintaining AI responsibly. It covers the risk management and data governance, human oversight, transparency, and life cycle management. The second standard we have is IEC 23894 that discuss about the risk management. So it gives us the structured process for identifying and managing AI specific risks. That includes data bias, distributional shift, and model drift. We will discuss these risks in detail in our future sessions as well. Third one is EU AI Act, European AI Act. That's a regulatory framework. AI used in critical infrastructure, which railway is clearly a safety critical infrastructure, as we have discussed in our first or second slide. So, EU AI Act has classified rail as a high risk sector and which is subject to strict documentation and monitoring and conformity requirement. So, railways is classified as a high risk category. There are four total risk categories identified in EU AI Act, and railways are in the high risk critical safety critical infrastructure. And then we have few complementaries here provided to us by RSSB toolkit, Rail Safety and Standard Toolkits. First one is T1363. It's about AI Change Toolkit that provides a question-based framework to assess implications of introducing AI, which is aligned with CSM-REA. That's a regulatory framework. I think it stands for Common Safety Method, risk evaluation and assessment. Yeah, common safety methods for risk evaluation and assessment. So that's the first toolkit. Second toolkit we have is 1364. That's the map of applicable standards for different rail AI use cases. And then third toolkit we have is about human factors, which is 1362, T1362. That is the practical principles for designing AI that empowers human, maintain explainability, and builds trust. Human factor we will be discussing in our sixth or seventh session in detail. So these are complementary, by the way. As a system assurance engineer, a system assurance specialist, you must use EN 50126, EN 50128, and EN 50129 as your primary assurance framework. Layer those with the newly published standards, which is IEC 42001 for governance and IEC 23894 for AI specific risk management. For reference, you can use RSSB, Rail Safety and Standard Board's toolkits for rail specific guidance. Ensure compliance with EU AI Act or any local regulation in your region. So let me summarize the key takeaways from today's session. First, AI is not a future technology in railways. It's already here, it's already deployed. Machine vision inspection, predictive maintenance, digital twins, obstacle detection, incident analytics, traffic management, all these are in operations, are active pilots around the world. Second one is there are genuine business and safety drivers. Maintenance costs have dropped, component lifespans have extended, inspection runs faster and more accurately, safety learning accelerated. For an industry under cost and safety pressure, AI is attractive. Third one, we discuss about AI introduces new challenges because having a probabilistic behavior, opacity, data dependency, and its drift, these are real and they complicate assurance. A safety engineer can't just apply the same mindset as for traditional hardware and software. Fourth one, and this is crucial, the existing standards still apply, like EN 50126, 128, 129 are the foundation. They mandate the right processes, hazard analysis, FMEA, requirement traceability, VNV, and safety cases. If you apply these rigorously and adopt them from AI-specific consideration, you can assure AI in railways. Fifth, we discussed about some new standards and frameworks that have emerged filling the gaps. First one was about 42001, IEC 42001, that was for the AI management, in other words, AI governance. Second one was IEC 23894, that was for AI risk management. Then we discussed about EU AI Act and how railways was classified as a high risk. That's for the regulation. And then some RSSB rail safety and standard toolkits as well. This is just the beginning. Over the next series of sessions, we will dive deep into each of these standards, explain how to do HARA, hazard analysis and risk assessment, and FMEA, failure mode and effect analysis for AI solutions. We will discuss human factors and ethics in details, and we'll walk through a practical implementation roadmap for AI. By the end, you will have a comprehensive toolkit for assuring AI in railways. Thank you very much for your attention during this session. I hope the session has given you a solid introduction to AI in railways, not just exciting possibilities, but the real assurance challenges as well. In the coming days, we will discuss more topics. In our lecture 2, we will have a deep dive into standards like EN 50126 and the RAM's life cycle in depth. We will talk about how reliability, availability, maintainability, and safety are defined and balanced in the presence of AI. Then, in our section number 3, the lecture 3, we will explore the new standards for 2001, 23894, EU AI Act, and RSSB frameworks. You will learn how to map these into the existing rail standards and build a coherent assurance strategy. And then in lecture 4, I think we'll focus on AI in maintenance. We'll discuss about machine vision, predictive maintenance, digital twins, and dive deep into RAM's implications. And then further on from lecture 5 to 8, we will cover safety, operations, human factors, risk analysis, and implementation. So if you have any question, please ask. Otherwise, we will see you in the next session. Thank you.
All right, that's it for this session. If you found this helpful, hit the subscribe button and turn on notifications so you don't miss the next one. And quick reminder, make sure you check out the podcast series here on the channel, Rams Ready for Everything Rams, and Safe Tracks for System Safety Assurance. If you're following along with this course, those episodes will really help connect the dots. Thanks for watching and stay tuned for the next one.